Okay. Hello everyone, let's get started. Okay, we need to go very fast today. Hopefully we can finish this chapter 3.4 now. Okay, and yeah, so starting with chapter 3.4. So 3.4 is about basis, and as we have said in 3.3, basis is this thing. So basis is the idea that we have for minimal spanning set. So in 3.3 we discuss this idea of minimal spanning set where so vector are the smallest number of minimal spanning set is a set of vector where you remove any of them, you are spanning a smaller set. Okay, so it's a minimal spanning set. And we prove in this 3.3.0 that you are minimal spanning set if only if all your vectors, the set of vectors are linearly independent. Okay? And we say a minimal spanning set is also called a basis. Okay? And now we have a more formal definition. Basis for basis for vector space V is a set such that they satisfy two properties. First is that they need to be this set of vectors need to be linearly independent, as we say is a minimal spanning set, and also this set of vectors need to span your V. Okay, so yeah, so your so the vector need to be a spanning set for your V. Okay, so yeah. This also just remember for if something span V, that means that anything inside V is a linear combination of those vectors. That's the definition of span. Span is a set of all linear combinations. Okay, and so this is kind of so as we said, this is just extend what we said, but I guess the idea here is a bit of a reverse. So before we were saying that a minimal spanning set is more like an idea on set of vectors, and the basis is more like an idea for the vector space here. Okay, so the vector space. So for the definition of basis, we are more looking for a set of vector for a vector space. That's whether the set of vector is basis for the vector space. And there will be, as we'll see, there will be many bases for a particular vector space. And yeah, in particular, so maybe I should draw a picture here. So there are many different bases. So there are bases. So there are bases 1, 2, 3 different bases for your vector space. Okay. This is a vector space. Okay, and let's see a quick example. So if our vector space is R3, and then there are these easiest possible bases, the standard basis, that is just a set of standard vectors. So E1, E2, E3, they are the vector with 1, 0, 0, and 0, 1, 0, and 0, 0, 1. And there are other bases, and for example, those two are also bases. And you can check that this set of 3 vectors and this set of 3 vectors are also bases for R3. And we'll very soon see that. So the important thing here we want to see is that all those bases have 3 vectors, and this is something you can prove that. Any basis for any basis with finite number of elements will have the same number of elements if they are the basis for the same vector space. Okay, and yeah, let's see. Okay, so now starting to theorems. Okay, and to see this all the bases for R3 have 3 elements. We start first with the theorem 3.4.1. It says that. Okay, if we have a spanning set for vector space, if we have just any spanning set for vector space V with only n elements here, and if you have another spanning set that has more elements, so another spanning set. Oh, sorry. So we sorry, the theorem is a bit even stronger. So if you have any other set of vectors, so we don't even say spanning set. So we have any other set of vector in space V that has more number than your number of vectors in your spanning set, so n bigger than n, then this new set of vector is linearly dependent. Okay, and yeah. So this any collection of n vector. I guess we should say any set, but okay, this is set we'll call then U. Okay, U1 to UN. So we'll have then here. Okay, so this is U1 to UN. Any set of n vectors in in V, they will be linearly dependent. Okay, and below spoiler, we are going to use this to show that this U1 to UN is not going to be a basis for V, because because as we say, we want if a set of vector is a basis, they need to be linearly independent. Okay, because this set of U is linearly dependent, they are not a basis. Okay, and yeah, let's start with the proof. The proof is a bit complicated. So we have a U1 to UN vector in V, and we have V1 to Vn that span V. So we will use the fact that V1 to Vn span V to express all those U as V. So it's quite a natural thing to do. So you have every Ui, so I from 1 to n can be expressed as a linear combination with V. And so we have a notation for those linear combination coefficients. So AI1, AI2, all the way to AIN times V1, V2 to Vn. Okay. So those are just real numbers that represent the coefficient to represent Ui as a linear combination of Vj. Okay. So yeah. Okay. And now we want to check whether U1 to UN is linearly independent. So we check this equation. So we check this linear combination of UN. Want to see whether this equation has a non-trivial solution. So C1U1 plus C2U2 plus all the way to CMUN. And so this expression we want to check whether it is equal to zero vector. And now we use our decomposing theorem of U equal to V. So this will be linear combination. This become linear combination of V, and with a whole bunch of C and A inside. So you have C1 times this summation J A1J, and C2 summation J A2J, etc. Okay. And so we have summation. Then usually the thing we want to do is we want to change the order of summation. Okay. So we have sum J here, and everything has sum J, so we can pull sum J out. I guess yeah, everything has sum J, so we can pull sum J out, and we can also write more succinctly. So we have this C1, C2 to Cn. So we also have this summation here written as a summation over I, where I from 1 to n. Okay. So in the end, we have this sum J, sum I, and then Aij and Aijci and times Vj. Okay. And as we said before, we want to check whether this thing equal to the zero vector or not. And so this is a zero vector. Let's write it in vector side. Okay. And then we look at this thing. Yeah. Sorry. And so we have something here that we should write. Okay. So. Okay, so this thing here is now sum over coefficients on Vj. Okay, and so here we use the fact that sorry, let me see. Spanning set. Okay, never mind. Okay, so yeah, so we have sum over coefficients of Vj, and we want this to be zero vector. Okay. Okay. I think probably won't. Okay. Yeah. For now, let's assuming this is a bit annoying. Okay. I guess for now, because this doesn't matter. Let's assuming B1 to Vn is actually a basis. I think it's a bit easier to prove. Okay. Basis, so that is also linear independent. Okay. And so now we have some over coefficient Vj and want it to be 0. Yeah. And so if we want this thing to be 0, then this thing is equal to 0. And then now we can use that Vj's are linearly independent. So Vj's are linearly independent, then all those coefficients must be 0. Because you have a linear combination of a linear independent thing equal to 0, then the coefficient equal to 0. Okay. So now we have a whole bunch of equations, or a whole bunch of equations saying things are equal to 0. Okay. So we have that summation I from 1 to so for every Vj we have a coefficient here equal to 0. Okay. And every Vj we have the coefficient equal to 0. And yeah, so we have an equation for j from 1 to n, and it says this is equal to 0. So sum I from 1 to n, sum over I, and aij ci equal to 0. Okay. So sum over I, aij ci equal to 0. And we can think about these n equations as a linear system of equations. Okay. So I should say linear here. Linear system of equations. Okay. We have a linear system of equation here, and where these aij here are coefficient, and ci here are unknown. And then finally we can use fact that m is bigger than n here. Okay. So if we write down this linear system of equation as a matrix, then we have this matrix, which is actually a transpose of A, and it has we have n equation here and m unknown here. So those ci's are unknown because I from 1 to n we have m unknown here, and then we have those aji as a coefficient of this matrix. And whether it's aij and aij or aji here is not too important. What's important here is that we have more unknowns than equations. Okay. And this is also a homogeneous equation because every equation has equal to 0. Okay. So if you think this set of equation as a linear system equation, it has is a homogeneous system with more unknown than equations. And by theorem 1.2.1, we have that this system must have a non-trivial solution, a solution that not OC equal to 0. Okay. And yeah, this is a bit of a review of this homogeneous underdetermined system. It says that if you do Gaussian elimination, then you see that there must be some free variable, and because there is a free variable, then there are infinitely many solutions, so there are non-trivial solutions to your homogeneous system. And we know it's homogeneous system, so you must have solution. Okay, so yeah, so this thing has a non-trivial solution, and finally we put things back to our yeah, finally we put this thing back to our U. Okay, so our non-trivial solution are those C hat, C1 hat, C2 hat to Cm hat, and but we say that where do we get C from? Okay. And yeah, we get C from this linear combination. We say C1U1 plus C2U2 plus CnU1 equal to 0, and yeah, so let's satisfy the equal to 0, and we see there is a non-trivial solution. So we see that there is a non-trivial linear combination between U that give you the 0 vector. Okay. Yeah. Oh, I guess here. Oh, sorry, I got confused myself. Okay. So we don't really need linearly independent here. That's sorry, I got confused myself. Okay, so I want to just okay. So logic is a bit different. Okay, so let's erase this. Sorry. So we don't really need linear independent here. We just need we have a solution. Okay, so. Yeah, so this is, sorry, so because this is actually a constructive proof. So we are solving this thing to find a solution, non-trivial solution such that the linear combination of u equal to 0. Okay. So we are trying to solve this equation for a non-trivial solution for Ci. Okay. So we have this expression here and we'll try to solve for this thing equal to 0, this set of equation, whether they have a non-trivial solution. And we do find, so by this theorem 1.1.2, we do find that we can have a non-trivial solution of this set of equation. We can make all those terms equal to 0 by solving this linear system equation and finding a non-trivial solution for C. Okay, so we have some non-trivial C hat such that the linear combination of U with C hat will become the sum of 0 coefficient on those V vector and equal to this 0 vector. Yeah. And yeah, so we see that we find a non-trivial solution such that the linear combination of U equal to 0 vector. So we have explicitly shown that U1 to UM are linearly dependent. Okay. Yeah, sorry for the mix up. So this is theorem 3.4.1. We see that if I have more vectors than a spanning set, then this new set must be linearly dependent. Okay. Okay. And yeah, so we want to see whether this is equal to 0, this is equal to 0 or not. Okay. And anyway, this is our theorem, and from here we can show something very nice. We show that any two bases for the same vector space V must have the same number of elements. Okay, and this is just follow directly from our theorem before. So if this U has more vectors, so if M is bigger than N, then we know U are this set of vectors here are linearly dependent because we know basis has okay. So basis need to satisfy 2C. They need to be Li. And they need to span B. Okay, and so we do this in two directions. If both of them are bases and N is bigger than N, then this span V. So we know this span V. Then we know that this cannot be Li because the theorem, the previous theorem says that if this span V, then this cannot have one vector. Okay, so N cannot be bigger than N. And we can have other way around because this span V, then N cannot be have vector, then V cannot have more vector than U because from the previous theorem. Yeah. And yeah, so by doing this two-way, we see that N must be equal to M because none of them can have more vector than the other. Okay, so use one of them being span, then another one being Li cannot have more vector, something like this. Okay, and now because every basis has a same number of vector, we can define this idea of dimension. Okay, so finally now we can say dimension of R3, R2, etc. So dimension is the number of vector in the basis, okay, of a basis. Okay. And but there is a special case. So there is this special case of this space of only 0 vector. So this space of only 0 vector. It has one vector inside, but it kind of don't need anything to be a basis. Okay, and so this thing is special case. It has dimension 0. So it's basis kind of have no vectors. Okay. And but yeah, but if your vector space can find a basis, and if your bases have n vector, then then it has a dimension V. and sorry, has dimension n. Okay? And yeah, that's when your basis has a finite number of elements, and sometimes your that's a finite dimensional. Okay, if you have a finite set of vectors span V, and otherwise sometimes your vector space is infinite dimensional, but we don't deal with that too much. Okay, it's weird to define the dimension of infinite dimensional vector space. Okay? But in, yeah, I think in most of our course we deal with a finite dimensional vector space, where everything is nice and you can find a finite set that spans your vector space. Yeah. Okay. And so a bit of notation here. So for this dimensional V, sometimes we write it as this mathematical term. Okay. So it's just a dim V, dim for dimension. Okay. And a few quick example of dimensional vector space. So you have a vector space that's spanned by one vector in this R3, and this is one-dimensional vectors, one-dimensional subspace or the one-dimensional vector space, and it's a line. So a line is one-dimensional, like our intuition. Just like as our intuition. So the span of only one vector, one-dimensional. And then we have a span of two vector, and it's this plane, and it's a two-dimensional subspace of R3. And finally, you have three vectors that are linear independent, therefore they are not on the same plane, and it will span the whole R3, and it's a three-dimensional vector space. So you see that Rn n-dimensional vector space. Okay, so this is technically a theorem, but they are quite intuitive. And the subspace of a line is being one-dimensional, and the plane being two-dimensional, and the space being three-dimensional, also fits our intuition. Okay, so that's the idea, the concept of a dimension of a vector space. Okay, so in R3, those just follow our intuition of dimension in physical space. But if you want to talk about dimension of abstract vector space, and then you need we have this more abstract definition where the dimension is the number of vectors in your basis. Okay. And yeah, then let's go to a very important theorem about basis. Okay, so we define our basis as so you have a vector space of dimension. We define, I guess at the start of this section, we define basis as a set of vectors that has two properties. We say they need to be linearly independent, and they need to span your vector space V. That's a basis. And just from the theorem before, we see that if your set satisfies those two things, then your basis and all basis has the same number of vector. That's n. And actually, in this theorem, we show that any two property here will mean you are a basis. So basically, any two of the property here will mean the third property. If you have so we fix a vector space V, and any set of vector inside V that has those two properties will give you the third property. So first one we have that your set of number n and your LI, and that will give you span V. And then second one will say that span V, and you have n vectors, and it will give you LI. And that means that any two of these conditions give you a basis. Yeah, so it's very important. Especially important to remember the result, and yeah, also nice to remember the proof. Okay, so let's see the proof. So first one, we have an n vector, and they are linearly independent, and we want to say they span V. Yeah. So yeah, so we assume our set of vector are V1 to Vn, and remember our dimension of V is n. Okay. And yeah, so we have any set of vector that's Li. And we want to say that span V, so we just put any other vector V, small v in big V. And basically we want to show this small v can be written as a linear combination of V1 to Vn. That will mean that this V1 to Vn span this V. Okay. And yeah, so we consider the set of vector that's your v1 to vn and extra vector v inside this v. And we show that they must be linearly dependent. They must be linearly dependent because from, I guess, the theorem we just showed. Okay, is from kind of a theorem 3.4.1. Okay, because because v1 to vn already span v, and you add the extra vector, then they must be linearly dependent. Okay, so this is theorem 3.4.1. Okay. And since they are linearly dependent, so we can write down this linear dependent-independent equation and find a non-trivial solution. So C1V1 all the way to Cn plus 1V, and this is equal to 0 vector with a non-trivial solution. And in particular, this non-trivial solution must have that this extra coefficient Cn plus 1 being non-zero, because if you have Cn plus 1 equal to 0, I guess any solution here, Cn plus 1 must be I guess here I should say here non-trivial. Okay, so if you want C1 to Cn plus 1 being non-trivial, then Cn plus 1 must be non-zero, because you have this 0, and so then if you don't have this term, then and you have this thing, we have a non-trivial solution, then your v1 to vn are not linear independent. Okay, so if you want C1, C2, etc. be non-trivial, then Cn plus 1 must be non-zero. Okay, but if Cn plus 1 is non-zero, then we can move v to other side and divide everything by minus Cn plus 1, and then we got v as a linear combination of other things. Okay, so we can do this because Cn plus 1 is non-zero, so we can divide by Cn plus 1. And so we see that v can be written as a linear combination of other vectors. Okay. And so that means that any v can be written as a linear combination of this v1 to vn. That means v1 to vn span v. Okay. That's proof of first part, and then we have proof of the second part. We have any set of vector v, set of vectors that span whole space v. Any set of vector, set of n vectors that span whole space v, then they must be linearly independent. Okay, and let's see how this goes. Okay, so we have a set of vectors that are linearly. So here we do proof by contradiction. So we go other way around. So we fix that we have a set of vectors that have n vectors, and we go. So we want to go from span v to linearly independent. Then here we show that if you are linearly dependent, so we go to contrapositive. We go if you are linearly dependent, then you don't span v. Okay, and so we show. So we assume that your set of vectors are linearly dependent. Okay. And if you are linear dependent, then we can find something that's a linear combination of others. Okay. This is what we have talked about in linear dependence. Okay. Okay. So if you are linear dependent, I guess we, here is something we should pull a theorem later. Anyway, if you are linear dependent, we can find one of them as a linear combination of others. Okay, and assume that's Vn, then we can get rid of Vn from the set, and we will still span V. Okay, so this is something we show. I think this is something we show in 3.3.0. I don't exactly remember, but anyway. So something is linear dependent, and we eliminate it, and you will still span the same vector, because so we have done this calculation in 3.3 where we see that any linear combination with them, because the Vn can be written as a linear combination of others, so you can just written as a linear combination of V1 to Vn minus 1. Okay, and yeah, and so this elimination process is actually also very important. So this elimination process is something we'll keep arguing. So this is how we can get LI set from another LI set. But anyway, we can keep doing this, and we will get at some point we will get a linearly independent set. So V1 to Vk that are linearly independent. Because yeah, we can eliminate. We can keep doing this elimination until we get the LI set. Okay, and yeah, so because there are finite number of elements, so we must stop somewhere. Okay, and at the end we have a basis for V, and but this basis will have a dimension k less than n, and that's a contradiction, because we know, yeah. So at the end we'll get this thing that's both LI set and also still span V. So that's a basis for V, but k is less than n because we have eliminated some vectors here, and that's a contradiction. Okay. And so we see that this set of n vectors must be linearly dependent if we want to span the whole space V. Okay. And so we have a bit of an example of using this theorem. So we want to check whether the set of three vector is a basis for R3, and yeah, and now if we want to be a basis for R3, by just definition, we need to check that they span R3 and they are linearly independent. But now we know that R3 is dimension 3, and we have a 3 vector here. So we only need to check one of the two property here. So here we check that they are linearly independent, and from previous section we know that we can just check because we can check that the determinant. We can check whether the determinant equal to 0. And because the determinant is not 0, we know they are linearly dependent, and it's a basis. Okay. And yeah, we have 20 minutes. I think we can finish this section. Okay. So before we go to next theorem, we want to have a very nice lemma here. I think this lemma is even a bit more important than a theorem. And actually, this lemma is something we can talk in 3.3, but we delayed here. Okay. So this lemma is only about linear independence. So we have that you have a set of vectors that are linear independent, and so I want to see whether when do you add a HR vector that the bigger set is still linear independent. And yeah, this is kind of if only if direct. This is actually a if only if statement, but we only prove one direction. So we say that if Vk plus 1 is not inside the span. Okay. So if it's another linear combination of this thing, then you add this HR vector, then the new set is still linearly independent. Okay. And kind of the negation of this statement is quite obvious. If Vk plus 1 is inside span, then it's a linear combination of those things, and this thing will not be Li. Okay. But anyway, let's prove this statement. So if you have something not inside span, and then you add this thing into your set, then you still have a linear independent set. Okay. And yeah, so we go by definition. We check the definition of your set, whether this linear combination equal to 0 has a non-trivial solution. Okay. And so we want to solve for this equal to 0, and if you have ck plus 1 equal to 0, if you have ck plus 1 not equal to 0, then yeah, I see. I guess so here I should say we want to find a non-trivial solution. Okay, so here we're trying to find a non-trivial solution of this equation. Okay? And if our non-trivial solution have ck plus 1 and not equal to 0, then all other things then we just have the this linear combination for v1 to vk. But we know v1 to vk is linear independent. Okay, and yeah, so we have just a non-trivial solution for v1 to vk linear combination equal to 0, and that's a contradiction of them being linear independent. Okay, and yeah, I guess I don't need to write. Yeah, I don't need to write negation here. Here, this part, I should write this part. Okay, so this part we can just say by linear independence of v1 to vk, or the c1 to ck will also be 0. Okay, so we only have sorry, I got confused myself. Sorry, that's the next part. Sorry if sorry, I got confused myself. That's the next part. Okay, so yeah, so we want to see whether this thing has any solution, and so we are actually not finding non-trivial solution. Sorry, I forgot the logic here. Okay, so yeah, sorry, restart. So we want to solve this equation, and if ck plus 1 not equal to 0, then we can do. Let's try to reuse. Okay, so we can do this thing again, and we can write v as a linear combination of others. So v as a linear combination of v1 to vn. I guess I should rewrite that equation. And so vk plus 1 as a linear combination of others, and contradict this thing. This contradict vk plus 1 not in span of v1 to vk. Okay, so sorry about the mix up. Yes, and so we know vk plus 1 must be 0 because it cannot be not 0. And if equal to 0, then we have an equation that just don't have this term, and that's a linear combination of v1 to vk. And we know that by linear independence of this thing, all the c1 to ck must also be 0. Okay, and so we will see that the only solution to this equation is that everything equal to 0. And yeah, so that means this new set is also linearly independent. Okay, so yeah, sorry for the mix up. Okay, and yeah, finally we show that the new set is linearly independent, and we can talk about the next theorem of this section. And yeah, I think this theorem is a bit funny. I think it's actually the proof is more important than result. Okay. What we really like this theorem is they are do two things: is extending a linear independent set, and trimming down a non-linear independent set until we get linear independent. Okay. And anyway, the actual theorem statement are two things. So once again, we have a vector space of dimension n, okay? And we say any set of less than n vector cannot span your v. And then second one, you have less than n linear independent vectors, then you can extend this set to become a basis for v. And also, if you have a set of vectors that's a spanning set, but you have more than n vector, then you can take a pair those vectors down. So basically, remove vectors from here and get a basis for v. Yeah. And yeah, so okay, and yeah, so we have 1, 2, 3 to prove. The first one is quite obvious. It's almost directly follow from theorem 3.42, where we say any basis must have n vectors. Okay. Yeah, and so we only need to do something to make this look like a basis. So we are missing a little bit here. So you have k vectors with k less than n. Okay. And yeah, but this is not a basis yet because they might be linearly dependent. Okay. So we want to eliminate some vector from here until they are linearly independent to show contradiction. Okay. So yeah, so we want to eliminate linear dependent vector from it. And we can do it because we're already done it. So it's in this proof here. Okay. So we say we can, if our set is linear dependent, then we can always find something that's a linear combination of others, and we can remove them, and they will still span the same set. Okay. So we can do this process over and over until we got the linear independent set. Okay. And when we do that, we will have even less vectors. We have some k-prime vector, and that's less than n. But this set now still span B, and they have length vector than n, and that contradicts our definition of dimension n. And so, yeah, that's a contradiction. So this cannot happen. Okay, so that's one. And then the second one, we will need to do extend. And we do extension exactly like our lemma is 3.4.4.0. Okay. So what we do is we have this set that does not span V, but they are linear independent. And from not spanning V, we can find some vector inside V that's not inside your span, right? Because the definition, your span is smaller than V. So we can find some bk plus 1. That's not inside span V, and that's a non-linear combination of V1 to Vk. And and then by our lemma, we know that the new set of vector is still linear independent. Okay? And so we can keep doing this. We can keep doing this until we have n vectors, and we know that by our theorem 3.4.3, if we have n vector, and we are linear independent, then we must have a basis. Okay. And yeah, then finally the third one is similar to the first one. So we have a set of more than n vectors that span your vector space, and we can keep eliminating vectors, and we can keep eliminating vectors without changing our span, and until we have n vectors, then we will have a basis. So you have n vector, and we span our vector space, then we have a basis. Yeah. So I guess here is eliminating without changing span. Without changing span. Okay. I guess here we can have a bit of summarize of the two processes. So we can do two things. We can add vectors, while so the two operations, that's very nice. Add vectors while staying linear, while staying Li. Okay. Oh, sorry, L and I. Okay. So add vectors while staying Li, or removing vectors while maintaining span, or removing vector. I guess remove. Okay. Remove vectors without changing span. Okay. Okay. Yeah, so those are two things you can do. So your set of vectors are linearly dependent, then you can keep remove vectors without changing your span. And you have a set of vector that's linearly independent and didn't span the whole thing, then you can keep adding vectors while staying linearly independent. Okay. And yeah, that's two nice operation, and we finished this section. So checklist for 3.4. We talk a lot about basis. So basis, by definition, is something that span your whole vector space, and is a set of vectors that span your whole space and are linearly independent. And we have the corollary 3.4.2 that define the dimension of a vector space. That's the number of vector of any basis for your vector space. And we have this very nice theorem 3.4.3 says that any two of those three conditions will give you a basis for your n-dimensional space. Whether you have n vector inside, or you are linearly dependent, or you span the whole space. And finally, in theorem 3.4.4, we see that there are two very nice operations you can do on your basis that you can do to your set of vectors. That if your vectors are linearly dependent, you can keep removing vectors while while having the same span. So so they are kind of doing on those two things. So you have too many vectors, and you span V, then you can keep removing vectors. You can keep removing vectors while stay spanning V. Or if you are linearly independent, but you have too little vectors, and you can keep adding vector while staying linearly independent until you span V. Okay. And then you can kind of feel that linearly independent must have less equal to n vector, and span V must have a greater or equal to n vectors. And if you want to satisfy both, then you must have n vectors. Okay. And we actually finished quite fast. So so we finished this section, and we can finish 3 minutes earlier, and see if you have any question. Otherwise, you can stop here. Okay. Yeah. So see you next Wednesday.